because there are no magnetic monopoles to move around in a current. But if there were, we could have magnetic currents as well. All right? And these would be the Maxwell equations in that context. And so I want to talk to you guys about some stuff. So that's one thing. If there was a magnetic monopole, then the divergence of the magnetic field would be 4 pi times the magnetic charge m, Dirac delta function of r. That would be a magnetic monopole at the origin. And then when I integrate over a Gaussian sphere, I would, lo and behold, I would get that the magnetic field, the formula for it would be B over what? 4 pi r squared, but no epsilon naught because we don't have any of those units. But so it would just be, yeah, it would just be, oh, I think I'm missing my 4, wait a minute. Did I put a 4 pi in there? I think there should be a 4 pi squared here. Anyway, it should be 4 pi squared. I've long since lost the LaTeX for these notes, so I can't fix it. But anyway, I wrote these in grad school, I think. So, all right. Whoa. I think I skipped like 30 pages. Oh, it's because I was way into the I was way into this document. Oh man. So I actually started with, I do want to go over some of the back matter here, because otherwise you can't understand the next thing I was about to show you. So these are regular Maxwell's equations, right? And we can derive magnetic field and electric field in terms of potentials like that. The curl of the vector potential. That might supposed to be a plus. I don't remember. I'm a little bit, well, there's another minus down here. Maybe it's minus. But you notice that the potentials are not uniquely defined, right? If I was to, shift, if I was to add a arbitrary function, I could add a gradient of that function to A. It wouldn't change the curl because the curl to gradient 0. And I could add a time derivative down here. Anyway, so the point is that if I shift the, sorry, I'm losing track where I am. If I could add a constant function partial t lambda to phi and a gradient minus gradient lambda to A, and it wouldn't change the curl and the gradient minus the time derivative. All right, so like if I shift A to A minus that gradient and phi to phi plus the time derivative of that same function, the end result is that I still generate exactly the same electric and magnetic fields. This is called gauge freedom. It's the fact that the potential is not uniquely fixed by the fields. That is not a contradiction to the thing I told you earlier about the potential being uniquely fixed by the charge density and its value on the boundary. It's a different discussion altogether, right? Like, you could fix different values on the boundary. Those would be different gauge choices, right? Like you have to fit the charge density in the inside. You have to have the Laplacian of your voltage function matches the given charge density function inside, but you could make the value on the boundary 10, you can make it 20, you could, whatever different things, you know? Anyway. So it turns out that special relativity, do you guys know what special relativity is? Just a little bit. Strings. That's a little bit further, but so in short, special relativity takes time and spaces to be, these are two different aspects of space-time, and Einstein mixes time and space into what we call Lorentz transformations or space-time translations. And anyway, I can't do all that here, but in short, what these pages show is that the formulas which define electromagnetism, namely Maxwell's equations, transform in a natural way under special relativity. Maxwell's equations are covariant with Lorentz transformations. In other words, they can be written in a tensorial form, which is to say that they can be written in terms of tensors. But what that means is that if you calculate a scalar like this, if you have covariant and contravariant, and these are summed over, it works out to b squared minus e squared. This is actually a physically interesting calculation because what it means is for electromagnetic field, if you calculate the value of the length of the magnetic field squared minus the length of the electric field squared in one inertial frame of reference, the value of that difference is the same in any other inertially related frame of reference. So this is the kind of thing that makes physicists happy because you can actually solve problems with these kinds of things. But anyway, these things can all be put together. You can put it all together in terms of the 4 potential. You can package the scalar potential and the vector potential together into a so-called 4 potential, which is a space-time vector field, a scalar field, I guess. Well, it's a vector field. What am I talking about? Voltage function, magnetic. So the voltage function that you guys perhaps know about, the vector potential that you don't know as much about, put them together into a 4 vector potential. And then you take that and you do this anti-symmetrization, and that gives you what's called the Faraday tensor, the field tensor. That has in it both the electric and magnetic fields. And so here's how that works out. This is just the, well, I don't remember what this is. I think I'm showing that the field tensor also doesn't change under a gauge transformation here. But now this is how to derive electromagnetism from an action principle, but you guys don't know what an action principle is, so I'm just going to go on. All right.
Is that on your Calc 3 notes?
This is not Calc 3. We have left Calc 3 far behind us.
This is your Calc 3.
This is not Calc 3. No. So I have proofs here that the Faraday tensor is in fact a tensor in the sense of transforming under Maxwell's equations. So basically if Maxwell's equations hold in one frame of reference, then they hold in another frame of reference is all I'm saying. All right, so Maxwell's equations transform in the natural way. But what's more fun is to rewrite these things in terms of differential forms and use so-called coordinate-free E and M. Here's the formulas for that. So after a bit, I introduce a one form. The one form potential has the voltage and the magnetic potential all together in one grand glorious thing. And when we take the exterior derivative of that one form, we get the Faraday tensor, which is a two form, which has the components of the electric and magnetic fields in there. And then you can derive Bianchi. Who cares? I'll get to, I gotta get, I'm sorry, I had too much in these notes. So anyway, long story short, you can rewrite all four of Maxwell's equations in terms of Hodge duality and the exterior derivative. So this is the co-derivative, which is a kind of close cousin to the exterior derivative. But the co-derivative of F is minus the current density, minus the forecurrent. This forecurrent is a combination of both the scalar charge density and the vector, the current the current density. And df. So these two equations are actually all four of Maxwell's equations, all at once. And no one cares. All right, let's go on here. Come on. So finally, we get back to the magnetic monopole. And I explained a bit in these notes about how that relates to something called the Hopf bundle. Hopf bundle is a fiber bundle. You might wonder what's a fiber bundle. Well, a fiber bundle is something that we basically have a space and we attach a group. You can think of it this way. You have a space, you attach a group over each point in the space, and then you allow functions of the space to carry representations of the group. And then as the group acts on the space, it can act in different ways at different points, but it has to act at different ways at different points in a way which is, in some sense, continuously connected. And your ability to change the group parameters at different points over space-time in some sort of coherent fashion, these are so-called local gauge transformations. And so Weil did something very interesting with this back in 1990, listen to me, no, a little bit earlier. 1919, Weil introduced, he said that you could actually make electromagnetism as a local U1 gauge symmetry, basically is what he did. He tried to do it actually as an external symmetry in the sense that he actually thought of space-time as being four-dimensional, but then also adding a fifth dimension, which was a circle, a literal fifth dimension. And that is the original theory of Weil. But the problem with that is it's kind of like a Kaluza-Klein type theory, and it has implications about momentum states and things which just aren't physical. And so Einstein pretty much talked him out of it about 1920 or so. He's like, no, this is like crazy. Your theory's just nuts. But there was something actually genius about it, because after some more work was done by Fock in London and some others, he came back in like 1929, 1930 and wrote down what we now recognize as the gauge theory of electromagnetism as a U1 gauge theory. It's kind of boring because you don't really need the full mathematics of the fiber bundle idea. So like part of what makes the fiber bundle interesting is that, well, to define a fiber bundle, to define so PFB is principal fiber bundle, you need a gauge group and you need a connection form. And it turns out like it's a Lie algebra valued 1 form. And so this Lie algebra valued 1 form plays the role like potential energy does, essentially. All right, it's essentially the potential energy of the theory. And for a principal fiber bundle, you can't generally just define this sort of analog of potential energy for the whole fiber bundle all at once. You have to define it on one part and then another part, and then where they overlap, they have to overlap in a certain systematic way. They have to transform in a certain very particular fashion. And it turns out that the way that the sections of a principal fiber bundle transform is exactly the same as the potential from physics had to transform. So like on the one hand, you had physicists discovering the theory of potentials for gauge theory that had to transform in a certain way. And at the same time, you had Hopf and other mathematicians discovering the theory of principal fiber bundles with the same mathematics. And about 1970, we all of a sudden realized, oh, wait a minute, this is the same thing. And so anyway, I could say more about this some other day, but I just wanted to show you guys, if you wanted to write down the analog of, well, if you want to write down the vector potential for a magnetic monopole, I have the formula in here. So that's the whole point of this, is that this is that's the potential that describes a magnetic monopole right here. So there's, in these notes I describe 2 different kinds of things. The one is a physical singularity, and the other one is an unphysical singularity. A physical singularity is something where there's actually charge, and no matter how you formulate the problem mathematically, that will be there. It's a defect. An unphysical singularity is a singularity which could be moved around depending on how you set up the mathematics. All right? And the Dirac string is an example of an unphysical singularity. And this thing, this of course is not defined when what? When r equals to 0, or also when z is equal to r, which is a fancy way of saying if it's along the z-axis in the positives. I think the positive z-axis has got that division by 0, right? But you could set this formula up to make that happen anywhere else from the origin. And so you could move that unphysical singularity of the positive z-axis somewhere else. It's just an artifact of the formula. The magnetic monopole is at the origin. That's where the charge is. That's where the topological singularity is. And this is what's meant by a Dirac string. It has to do with the vector potential for the magnetic monopole. And here I'm writing it in terms of like space-time stuff, unfortunately. I wish I had a more Calc 3 formula for it here right now, you know? But some calculation, I proved that the gradient is really the what you want for the monopole. It really does produce the field. Like I work it out here. Basically, this calculation shows you that the magnetic field components are literally reciprocal in distance. That's what we want for the magnetic monopole. Those are the formulas for the Coulomb type field for a magnetic charge would be that. These don't exist in nature as far as we know. And then I've got a bunch of calculations here. Anyway, principal fiber bundles are something that's beyond any course we offer here, right? It's beyond manifold theory. Like this is the next thing past manifold theory. Fiber bundles are really how to understand deeper things about manifolds, really. And topology, like a lot of fiber bundles were developed by Steenrod and others mid 20th century to understand some deep issues in topology. But it turns out that it's actually the same mathematics you need in order to properly understand the construction of potential energy functions for electric and magnetic fields. And it is a fortunate fact of our universe that we only have electric charge, which allows us to find voltage functions globally all at once without having this issue of domain overlap. If there were magnetic charges, we would have to face the issue of the Dirac string in our formulation of basic theory. We would have to define voltage, like magnetic voltage functions over part of the space, but not all of the space. And it wouldn't be something that was physically demanded. It would be something that's a mathematical artifact of the fact that you can't define it over the whole thing, much like you can't make a map that covers the whole Earth. It's that kind of thing. You're fundamentally limited to just look at a part. All of this said, I don't quite know how to set up the principal fiber bundle that does electric and magnetic fields at the same time, as I explain in these notes. But anyway, I think that's all I should say here. Next time we're actually going to get back into mathematics. This is just me talking to you about stuff, but I'll shut up now.